Continuing our discussions on kinetics, we're going to move on to the next type of rate law, which is the integrated rate law. And this is the first part. This one's going to deal with first and zero order reactions. So remember that rate laws are just a mathematical method for determining how fast a reaction occurs when you're given a very specific set of conditions. There are two types of rate laws. The differential rate law, which looks at concentration versus rate. And now we're going to talk about the integrated rate law, which looks at concentration of the reactant versus time. Now, in the integrated rate law, we only look at one reactant versus time. So the data that's going to be collected will be concentration of the reactant and the time elapsed. Graphing the data appropriately will be helpful. You may need to plot the data more than once by mathematically changing a set of data, but that's not really a big deal. So let's start with an actual example. This is the decomposition of hydrogen peroxide into water and oxygen. Here's the data collected. The time is in seconds, and the concentration of hydrogen peroxide is in molarity or moles per liter. When you graph the data, the concentration versus time, you see something that looks like this, which does not have a great line of best fit. As a matter of fact, it's actually a curve. Now, frequently, you can, quote, straighten up the curved line, unquote, by changing the value that you're going to be putting on the y-axis from the actual value to either the log or the natural log. And in this case, we're going to figure out the natural logs for each of these concentrations. Now you're going to plot the natural log of the concentration of peroxide versus time. And when you do that, the data looks like this, which is very obviously a straight line. Now the generic equation for a straight line is y equals mx plus b. And for this experiment, y is equal to the natural log of the hydrogen peroxide at any time t. The slope turns out to be the negative of the rate constant. X is equal to the amount of time that has elapsed, and the natural log of the hydrogen peroxide solution at time equals 0 is the intercept of b. So you can rewrite this equation as the natural log of hydrogen peroxide at time t equals minus the rate constant multiplied by the time you're interested in, plus the natural log of the hydrogen peroxide at time t equals 0. And just remember, the negative of the slope is the value of the rate constant. So generically, the first order integrated rate law is the natural log of some reactant A at time t equals minus k times the amount of time you're interested in, plus the natural log of that reactant at time t equals 0. If you graph out the natural log of A versus time and you don't get a straight line, then it is not a first order reaction. So now I'm going to give you a generic reaction and the data that goes along with that reaction. And then I'm going to ask you 3 questions. The first, is this first order with respect to A sub 2? Second, if the answer to 1 is yes, what is the value of the rate constant? And also, if the first question is yes, what is the concentration you expect of A2 after 15 seconds? So answer the first question, come back, check your answer, then I'll walk you through it. Go. And the answer is yes. How did we get that answer? We know for a first order reaction, if you graph the natural log of the concentration of A sub 2 versus time, you should get a straight line. So you need to calculate the natural log of the concentration of A sub 2. Just plug it into your calculator. You get these values. Then you graph it, and you see that that is definitely. So since the natural log of A2 versus time is a straight line graph, it is first order. So since the answer to question 1 is yes, now comes what is the value of k? Stop, figure it out, come back, check your answer, and then I'll walk you through it. And the correct answer is 0.0347 per second, or seconds to the minus 1. How did we get that? K is equal to the negative value of the slope. You calculate the slope in the normal manner, pick 2 points, and calculate it. I used at time 0 and time 10 seconds. So the slope is 0.347 divided by 10 seconds, which works out to be negative 0.0347, but k is the negative of the slope, so that becomes positive 0.0347, and k should always be a positive number. So we have the value of k. So now, what is the concentration of A sub 2 at time equals 15 seconds? Stop, figure out the answer, check it, and I'll give you a hint. There are two ways to figure it out, and I will show you both. Go. And the first answer I get is 0.882 molar. I did this one by utilizing the graph. I found 15 seconds on the graph and draw a line up to the straight line. I make a 90-degree turn and bring it over to the y-axis, where I see that the natural log of A sub 2 is equal to minus 0.125. So to get the concentration of A sub 2, I raise E by that number. When I plug that into my calculator, I get the concentration of A sub 2 equals 0.882 molar. But there is another way to get the answer, and that's to do it algebraically. We know that the general equation is the natural log of A sub 2 equals minus kt plus the natural log of A sub 2 at 0. We've calculated the value of k. We can see the value of the natural log of A sub 2. So at any time, this is the equation for this specific line. Plug in what else we know, which is 15 seconds equals t, and now the equation looks like this. Solve the equation, and you get the natural log of A sub 2 at time t is negative 0.1155. Raise E by that value, and you get 0.891 molar. So if you did it this way, the correct answer is 0.891 molar. But wait a second, you might say. Graphically, I got 0.882 molar. Algebraically, I got 0.891 molar. They're different numbers, and they are, mostly because the graphical is a bit more of an estimation. But if you do a quick error analysis to see the percent difference between the two numbers, you see there's only a 1% difference between the two values. They're essentially the same. However, there might be a third way to determine if this is first order if you have the appropriate data. And this involves an idea called the half-life. Now, the half-life of a reaction is the amount of time it takes up for a reaction to use up 1/2 of the reactant that is present. And it turns out that only first-order reactions have a constant half-life. Here is the data we had for A sub 2. I start at t equals 0, and I've got 1.5 molar. Looking through the data, I see that at 20 seconds, I have half the amount available, 0.750. I've used up half the reactant, so I can say that the half-life at this point is 20 seconds. So now I look at the 0.750, and it so happens at 40 seconds, I have half the amount of material again. The difference in time is once again 20 seconds. So the half-life stays at 20 seconds. Doesn't matter what the concentration is. The T1/2 is constant, so it's first order. Now, it only works if you have the data to show this. Sometimes the data may be found in a graph. Here's the graph of concentration versus time. I look at my point at time t equals 0. Here it's 1.50 molar. So I'm going to drop down to 0.750 molar. I'm going to go over to the line, and I'm going to drop down and see what time it is, and that's 20 seconds, so 20 seconds has elapsed. I'm going to half the 0.750, which is 0.375 molar. I'm going to go over to the line, drop down, and look at the difference between the two red lines, and that's 20 seconds again. The half-life is constant, so this is a first-order reaction. As far as half-life goes, for a first-order reaction, the half-life, the time of the half-life, is equal to 0.693 divided by the rate constant. This means if you're given the rate constant, you can figure out the half-life by simply doing the math. Given the half-life, you can figure out the rate constant by simply doing the math. And that completes our discussion about first-order reactions. Let's go to zero-order reactions. The differential rate law would be the rate equals K times the reactant A raised to the 0 power. So A to the 0 power is 1. So you can actually say the differential rate law is rate equals K. This means the rate is constant no matter how much of the reactant you have. And the integrated rate law is the concentration of A at times T equals minus kt plus a sub 0, once again a straight line equation, the negative slope is equal to k. And the half-life is not constant. It will vary with concentration. That's it for zero order. So to review, the integrated rate law compares concentration with time. We define A sub t as the concentration of the reactant at a specific time t. A sub 0 is the concentration at time equals 0. For a zero order reaction, the graph of the concentration of A versus time is a straight line. The integrated rate law is the concentration of A equals minus kt plus the concentration of A at time 0. K is equal to the negative slope, and the half-life is not constant. If you graph A versus time and it's not a straight line, it's not a zero-order reaction. And if the half-life is constant, it's not a zero-order reaction. For a first-order reaction, the graph of A versus time is not a straight line. Natural log of A versus time will give you a straight line. The rate law is the natural log of A at time t equals minus k multiplied by t plus the natural log of A at time equals 0. Once again, k is equal to the negative slope, just like for zero order, but this time the half-life is constant. It does not vary with concentration, and we can state that the half-life is equal to 0.693 divided by the rate constant, and that equation will be given on your cheat sheet. This completes our discussion of the integrated rate law as applied to zero and first-order reactions. In the next video, we'll deal with second-order reactions.